So we talked about resistors and circuits, we've talked about capacitors and circuits, now we're going to put them together. So that's why they're called RC circuits, resistors and capacitor in the same circuit. So think about what would happen here. When we first close the switch, electrons, little electrons, are going to come out of here, and they're going to go around, and they're going to build up on the negative side of the capacitor. And they're going to repel other electrons, sending them away, and then they're going to go back to the battery. So this side ends up with a positive charge. Different way of saying that is current flows from the positive side to the capacitor, and I'm using lowercase for what I'm going to do a little bit later. So current's flowing over to the capacitor, and it continues across. So really it's a break in the circuit. Current does not cross the capacitor. But because the charges are filling this up, and even if you want to think of it as positive charges repelling other positive charges across it until the capacitor fills up. Once this is fully charged, it can't handle any more electrons and sending away any more electrons. It will not allow current to flow anymore. So we're going to have a large amount of current and then less and less and less and less current, and we're eventually going to come up with an equation to describe that. So the two endpoints, a really good analogy sorry, is cars driving. If this is an empty parking lot, you get a big rush of cars to fill this parking lot, but as it gets more and more full, there are fewer and fewer cars. And if we include the resistor in the analogy, this is the really bumpy road that is slowing down the flow of cars in the first place. So they may not get there as fast because it's a really bumpy road, but the number of people that can fit in the parking lot doesn't depend on the resistor. That's just how quickly they'll get there. So for the endpoints, an uncharged capacitor in a circuit acts like it is a bare wire. It looks like current flows across it. Current doesn't flow across it. It's a buildup of charge repelling other charge. But it acts like, at the very beginning, a bare wire. A fully charged capacitor acts like a break in the circuit. And to illustrate this, I have a really fun circuit that I want to analyze. Another piece of tape. So I have a battery here and a switch. These are uncharged capacitors at first, 9-volt battery. And then I have 4 resistors. So resistor, and then this whole big network of craziness, and then back to the battery. So when we first close the switch, the uncharged capacitors act like bare wires. So I'm going to redraw the circuit without the capacitors and replace them with bare wires. So 15 ohms, 9 volts, 15 ohms, 5 ohms, 15 ohms. So what's the resistance of this circuit? Well, we have 15 in series with something. To figure out this something, notice current would split right here, this way or this way. When I got here, it would split and go this way or this way. So when current went across here, it would combine with this current, come back and combine with this current. So we have a 3-way split and a 3-way inclination. These are in parallel. So if I put that in the handy dandy calculator, 15 reciprocal plus 5 reciprocal plus 15 reciprocal, reciprocal the whole thing, this parallel combination has a resistance of 3 ohms. That's in series with this 15, so the overall initial resistance is 18 ohms. So the initial current through the circuit, from the battery, is 9 volts divided by 18 ohms, or half an amp. And then, a long time after S is closed. Well, now the capacitors are fully charged. When capacitors are fully charged, they act like breaks in the circuit. So again, if I redraw it, and I'm not even going to draw the lines that the capacitors are on, because if there's a break in the middle of this line, there's a break in the whole thing. No current can go that way. So now this circuit is 15 ohms and 15 ohms and 5 and 15. This is one series loop. It's drawn oddly, but this is all series. So the final effective resistance of the circuit is 3 times 15 is 45 plus 5 is 50 ohms. And so the final current is only 9 divided by 50 is only 0.18 amps. So current does continue to flow in this circuit. It doesn't completely stop because there's a path it can follow, but there's a lot less current because energy has been converted into electrical potential energy in the form of capacitors. And so a question might be, how much charge is stored on the 10? So if I add it back in here, and I'm going to use a different color because no current flows through here, 10 microfarads. So to remind you, charge on a capacitor is capacitance times potential. So, sorry, should have slid that up a little bit earlier. So the capacitance we know is 10 microfarads. To get the potential, it's not 9 volts, because this is not across the battery, but it does connect the points that go before the 15 and then the 5. So this is a series of 2 resistors, and they're in series, so it's 20 ohms. And you know for a resistor, V equals I times R. Well, we already know the current. It's 0.18 amps. And the resistance there is 20 that it's connected across. So its voltage is 0.18 times 20. And then if we multiply by the 10, 0.18 times 20 times 10, the charge stored on here is 36 microcoulombs. You could do the same thing for the 5 microfarad. It has the same potential difference because it also connects across the 5 and the 15 with 0.18 amps of current flowing through them. So you'd have the same voltage, just different capacitance. So not much point in repeating the same problem. So now we're going to go back to the first circuit because we need an equation. And hold on to your hats because there's going to be some calculus. So back to the simple circuit. Battery, switch, capacitor, resistor. So R, C, S, EMF of the battery. So we know current flows around this way because it goes from the positive side of the battery to the negative side of the battery, even though physically it's electrons going the opposite direction. So if we are in the middle of charging, there's some amount of current. It's less than the initial, it's greater than 0. That's why I'm using a lowercase. And there's some amount of charge built up on here, positive Q and negative Q. Sorry, trying to make that negative, not really working. There we go. So we're going to use the loop rule. So reminder, EMF across battery is, or voltage across battery is just the EMF. Voltage across a resistor is I times R, and we've got to do a negative or positive depending on direction. And then for a capacitor, remember the equation we just had, Q equals CV. So V equals Q divided by C. And again, this is the general equation. I've switched to, for this problem, the little q. So at some point in time where the current is little I and the charge is little q, this is the potential across the capacitor. So using Kirchhoff's loop rule, I am going to go around the circuit, and I think this is the marker that's dead. I'm going to go around the circuit starting here and go around clockwise. I always start at the lower left and go clockwise unless there's a really good reason to do something else. So when I start here, I go across the battery the normal direction, so I gain a potential of EMF, then bare wire, because of course the switch is closed, and then I get to a capacitor. And I have a potential drop across the capacitor because I'm going from high to low. I'm going from positive to negative. Here I was going from negative to positive. So I'm going to lose the potential across this, so Q over capital C. And then when I get to the resistor, I'm going with the current, so you already know that's minus I times R. And then I'm back where I started, so that's equal to 0. So I want something that tells me what's the current as a function of time, what's the Q, the charge, as a function of time. So any 3 seconds after I close the switch, how much charge is on the capacitor? Is it fully charged yet? How much current is flowing? So to do this, we're going to remember the connection that current is the derivative of charge, the amount of charge that passes by in a particular amount of time. So making this substitution, EMF minus Q over C minus dQ dt times R equals 0. The reason I'm doing some of these steps in this order is because I know what the answer is, so it's the quickest way, because it may seem kind of arbitrary. I'm going to isolate this left term, or excuse me, this term first on the left, so I'm going to keep it on the left side of the equation. Negative dQ dt times R equals, then I'm going to move both of these over to the other side. So I'm going to add Q over C and subtract the EMF. Now I want to get rid of R. I'm going to divide. Negative dQ dt equals Q over RC minus EMF over R. Now, I need that to be one thing. So if I do common denominator of RC, then this is already over RC minus, I need to multiply this by C. Okay. Now we're going to do this really neat math trick from calculus called separation of variables. I have a Q here that's the derivative of Q, and I have plain Q over here. So I'm going to keep my dQ on top, but I'm going to divide both sides by this numerator. So I get Q minus E over C equals, I'm getting rid of the dt by multiplying by it, and I'm taking the negative with it. And I'm leaving the RC in the denominator. So another way of saying that is I took this numerator and this denominator and I cross-multiplied and divided, and that's why they end up switching places. And I just kept that negative over here. Again, because I know where I'm going. So now I need to integrate this puppy. So the charge. Initially, the charge on the capacitor is 0. We're building up to some value in the middle of Q, and this is bad terms, but just go with it. So our final value is going to be Q. On this side, where time starts at t equals 0, and then we're interested in what happens at time t. So now we're going to integrate. Now, we are integrating a denominator, just Q. For those of you who are not in calculus, our polynomial rules don't work. And so the integral of dq over q, if you ignore this constant, the integral of dq over q is the natural log of q. Because we have a constant separated here, the actual answer is the natural log of that whole denominator. Those of you not in calculus, you'll get it eventually. Oh, bother, that wasn't on the screen, I'm so sorry. Okay, back to terms start 0q, 0t, you're good. Integral, natural log. So the natural log, and yes, it is absolute value of q minus EC, equals, now on this side, we're going to integrate, R and C are constants. So we're left with negative over RC, and then the integral of the integral of the derivative of time is just time itself. Now we have to evaluate these integrals between 0 and Q and 0 and T. So if I plug it in here, we get the natural log of Q minus EC, because we're, and this is where the notation is bad, we're putting Q in for Q and we're putting 0 in for Q. So minus natural log of 0 minus EC, so just that, equals, we put in negative T over RC, T in for T, and then subtract 0, which is just 0. So now let's remember an algebra thing. The difference of natural logs is equal to the natural log of their ratio, Q minus E over C over negative EC. And then we'll just get rid of that 0 over there. So, natural log of this expression. Got to turn the page. I'm just going to copy it. Natural log of Q minus EC over EC equals negative T over RC. Now, another property, the inverse function of the natural logarithm is the exponential function. Remember, e to the x is the inverse of natural log of x. Okay? So, if I do the exponential to both sides, it gets rid of this natural log. So I'm left with Q minus EC over, oops, I forgot to copy a negative sign, correct? Right, there's a negative sign in my denominator. equals, well, I raised this to the exponent, so I've got to do the same thing over here. And now we just have to do some cleanup. So I'm going to multiply through. So Q equals negative EC little e to the negative t over RC. Oh, no. The numerator is Q minus EC. I'm sorry. Numerator is Q minus E over C. I'm multiplying by the denominator. Now I'm going to add EC, and then I'm left with this. And then almost done. We're going to factor 1 minus e to the negative t over RC. And very, very last step. Remember, this was the EMF of a battery. This is the capacitance. Voltage times capacitance. This is the final charge. So Q as a function of time is equal to the final charge times 1 minus e to the negative t over RC. A graph of this, so this is exponential decay, but it's 1 minus exponential decay. So it's a exponential growth to a maximum, where this is QF. So this is Q of t. So we start with no charge, we build up to a final charge, and after enough time, we say we reached it. Now, another thing we used was that current, we know, is equal to the derivative of the charge function. So I can get my current function here. So I'm going to take actually a derivative of this one. I'm going to go back to this version of the constants, and you'll see why in just a moment. So these are constants, so they keep them on the front. And then I've got to take the derivative of this whole expression. Now the derivative of 1 is just 0. Minus, again, those of you who are not in calculus don't know this, but the derivative of an exponential is itself. So I'm going to do e to the negative t over RC times the derivative of the up top part. So t is our variable we're taking the derivative with respect to. So the derivative of this thing is negative 1 over RC. So we get a whole bunch of cancellation here. We have EC in the front. I'm going to put over RC, 2 negatives, so they cancel out, and we get e to the negative t over RC. Well, notice C cancels. That's the EMF of the battery and the resistance of the resistor. So this equation is the initial current, and it is regular exponential decay. And let's see, there's I, and let's go back and box this one. So the current over time starts at some maximum initial value and does the exponential decay. And notice they're like half and halves of each other. And this should be just like what you saw in the lab. You weren't graphing charge and current, you were graphing the potential, but potential is charge divided by capacitance, and potential is current times resistance. So multiplying or dividing by a constant, you get the same shape graph. So one more thing to talk about. Discharging a capacitor. So turn the page. Another circuit. This is a fully charged capacitor. So it has positive Q and negative Q initially. And I started to draw the wrong thing. Don't worry, that's later. So we have a switch, which we're going to close. And as soon as we close it, the positive charges are going to go around to the negative charge, causing discharging. We're providing a way for all of these positive charges that are collected together. Really, all these electrons that are hanging out here who really don't like each other now have a way to get back someplace else and to separate as far as they can. So when we apply the loop rule to this one, we gain across the capacitor. So we have positive Q over C, and then we lose across the residual, negative IR, equals 0. The math here is actually slightly simpler. We do have that in this case, the current is negative rate of change of charge. And that is because as the charge is decreasing, the current's going this direction. So that's why we have to introduce the negative sign to make this work. So we end up with a differential equation that looks like Q over C equals negative dq dt times R. And we do the math again, and I'm not going to go through it again. It's only slightly different. And we end up with these two equations. Q is Q initial times e to the negative t over RC. And I is, lowercase. I is initial current times e to the negative t over RC. So our charge graph starts from some maximum and goes to 0, which makes sense. We're discharging it. We're getting rid of the charge. Our current graph also starts from some maximum and goes to 0 because there's going to be a lot of current. Those electrons are really excited to get away from each other, and then there's less and less reason to get away from each other, and then there's no reason to get away from each other when it's not charged anymore. So we have the same equation both for charging and discharging for the current through the resistor. Starts from a high value, goes lower. For charging the capacitor, we have the increase to some maximum, and discharging is maximum down to 0. So same shape, but flipped over. So finally, you've got to be able to put this in the calculator. So just as an example, let's figure out Q. Let's say that the resistance is 100 ohms, the capacitance is 200 microfarads. So we're going to get R times C is 100 ohms times 200 microfarads. So we're going to get 100 times 200 is 20,000 micro something. We'll deal with the something in a second. But first let's deal with the micro. Micro means 10 to the negative 6, and we're already on 1,000 of those. So this would make a lot more sense to divide by 1,000 and move this up to milli. So if you're not seeing that, put this in your calculator with 10 to the negative 6, this in the calculator 10 to the negative 3, you'll see they're the same number. So now let's deal over here. Let's go back to an ohm times a farad. So no prefixes, I'm just doing units. So an ohm came from resistance, which is voltage divided by current. So its unit is volts divided by an amp. A farad came from capacitance. Capacitance is defined as Q over voltage, charge over voltage. So this is coulombs over potential. So those cancel. Well, I'm left with C over A. Well, an amp is a coulomb per second. So a coulomb divided by a coulomb per second, if we rewrite it, coulomb times second over coulomb, this is a second. So this was 20,000 microseconds, or 20 milliseconds. That's why, and you saw this in the lab, this is called the time constant. This gives the curvature of the graph to show how quickly it's going to get. And it's affected by both of these things. Unfortunately, in that simulation, I could only change it only allows the capacitance to be changed. So the resistance does affect how quickly or how slowly you charge or discharge the capacitor. It doesn't affect how much charge ends up in the capacitor, but it does affect how quickly, because it's in seconds. This time constant idea. So let's do a problem with continuing this. If we have so if we connect to this to a circuit that has an EMF of 5 volts, I think these are all numbers from the lab, that's pretty funny, 5 volts, and I want to know at t equals 10 microseconds, what is the charge? So, and this is while it is charging. So while it is charging, I use Q of t equals Q final, 1 minus e to the negative t over RC. Well, Q final is going to be C times V. So 200 micro times 5. 200 micro times 5 is 1,000 microcoulombs, which would be better to write as 1 millicoulomb. So this is 1 millicoulomb times 1 minus e to the negative 10 milliseconds divided by RC is 20 milliseconds. Now this has to be a pure number. Because that's in milliseconds and this is in milliseconds, I can put them in it directly as well. I could write 10 to the negative 3 and 20 to the negative 3. It cancels out. But these have to be in common units. So now in my calculator, what I'm going to do, and let's pretend I don't know that I can simplify that to be 0.5. I am first going to enter negative 10 divided by 20. And then I'm going to hit the E button. I'm sorry, I meant to say I was talking about my class calculators. We need the base E button, which is where? Right up here above natural log. Okay, see it's the shift. So I'm going to hit 10 negative divided by 20 equals. So I finished that. Now I'm going to hit the e to the x button because it's going to do e to whatever's on the screen. So shift e to the x. So that's that number. Now I need to subtract that from 1. So I'm going to make it negative and add 1 to it. So I finished the parentheses, and now I can multiply by 1 milli, which is trivial. So this is 0.393 millicoulombs. That's how you put it in the calculator. Now, if you have one of these calculators, you type it exactly as it's written. So I would do 1 times, open parentheses, 1 minus e to the x, and in the parentheses, negative 10 divided by 20. Close that parentheses, and we get the exact same answer, 0.393 millicoulombs. So we're about, since this ended up being 1, you can see that when we are at half a time constant, the time constant was 20, we're at half of that, only 10. Half a time constant, we have almost 40% of the charge already built up because it builds up quickly and then it levels off. It is generally accepted that it takes about 5 time constants to fully charge something. But you'll have more practice with these numbers on the Schoology assignment.